So good morning for those on site, and good morning, good afternoon, or good evening for those attending online. So welcome for the RISC-V virtualization tutorial, and thank you for taking the time and the interest to attend this tutorial. Well, the idea of this tutorial is to cover the broad spectrum of virtualization related to RISC-V. I took a good number of hours to put everything together, so I hope this is helpful. Sorry. Okay. This is the agenda for today. So it will be split in 4 big parts or 4 big topics. The first one is we will overview the RISC-V hypervisor extension, which is the extension to the privileged architecture to support hardware virtualization. So I will cover the specification, the different hypervisors, the different cores, open source and commercial, that already embedded this extension. And I will run a couple of demos and provide different pointers so that if you want to have a try, you can do it by yourself. Well, the second part of this tutorial is the RISC-V AEI, the Advanced Interrupt Architecture. The idea is to cover the specification, as well the different components of the specifications, the APLIC, the IMSIC, to discuss a bit the virtualization, and also to run a couple of demos. The third part of the tutorial is the RISC-V IOMMU. I mean, hardware virtualization support at the CPU level is important, but if you don't enforce, if you don't provide translation also for the I/O, it's a missing piece of the puzzle. So the idea is to cover a little bit and overview the specification, to describe the virtualization, and to run a demo based on the proof of concept components that already exist. And last but not the least, just to touch upon the nested virtualization and overview what has been done, discuss a bit what is the proof of concept at the moment, and discuss a bit the existing limitations and the potential work that can be done. Well, and without further additional delays, so I will just try to share 4 slides to introduce the audience to the concept of virtualization. So what is virtualization, for those not so familiar with this technology? Virtualization is an enabler technology to run multiple operating systems, coexisting operating systems, isolated operating systems, on top of the same hardware platforms. A kind of good analogy that you can do is that an hypervisor, also called virtual machine monitor, is to an operating system what an operating system is to a process. People are quite used with Linux that you will run an operating system to run multiple processes atop, so we run an hypervisor to run multiple operating systems atop this hypervisor. And virtualization technology is quite well established in different market segments and has a broad range. So it starts in servers and clouds for balancing, load balancing, and power management. We run hypervisors also on desktops when, for example, we want to develop in a different target OS, a top one that's running atop our machine, or in embedded or mixed criticality system is also widely used for isolation, consolidation, and security. And here on your right, on my right as well, we have 2 figures that more or less illustrate the different types of hypervisors. On the bottom, we have what is called type 1 or bare metal hypervisor, where you run your hypervisor or virtual machine directly atop the hardware platform, and then you run the multiple guest operating systems atop your hypervisor. This is the kind of architecture or topology that you can find in embedded and max criticality systems. On top of this image, we have the type 2 hypervisor, also called host hypervisor. And as the name suggests, basically you run your hypervisor atop your host operating system, which enables you to run multiple operating systems atop your hypervisor. You are pretty familiar with, for example, VirtualBox, VMware, when you run on your target machine, so that you can run different operating systems on your machine. Well, just a quick overview about virtualization in terms of techniques and terms. So yeah, the concept of virtualization was introduced quite long ago in 1974 with this famous paper from Popek and Goldberg. where they introduced the concept of classic virtualizability. They basically define the different features of virtualization, and they classify the instructions as privileged, sensitive, and innocuous. And the point here is that one specific computing architecture is classically virtualizable if the sensitive instructions are all privileged instructions. And this is quite important for one of the first established virtualization techniques, which is trap and emulation, that basically leverages ring compression. And you have here on the right, on the bottom, typically processors as, for example, two privileged modes: the kernel mode where you run your operating system, and then the user mode when you run your application. So by leveraging trap and emulation, what you do is you run your hypervisor or virtual machine monitor on the kernel mode, and then you deprivilege your guest operating system to user mode. And if the architecture is classical virtualizable, means that each sensitive or privileged instructions, when the operating system running in user mode wants to execute them, they will trap to kernel mode, where the hypervisor will basically decode the instruction, interpret the instruction, emulate the instruction, and then provide the result. And this is pretty much what we have in this image on the top right side, is the concept of trap and emulation. Then, because trap and emulation is a process that impacts performance, more or less depending on how it is implemented, we start to see the rise of paravirtualization. And in paravirtualization, what you do is basically you instrument your guest operating system, you change a bit your operating system, so that you can, instead of let the operating system run the instructions and trap to the hypervisor, you made explicitly calls to the hypervisor so that you get the result and don't go through this process of trap and emulation. And this speeds up a little bit the performance of the overall virtualization infrastructure. Well, but what we have been witnessing in the last decade was that virtualization gets so famous, so well established, that the mainstream computing architectures start to introduce hardware to support virtualization. And this has been done in Intel, ARM, and all the other mainstream architectures. And this hardware virtualization support, which basically alleviates a lot the performance impact, is done at the CPU level, which also includes the part of the memory with the memory management unit, but also at the interrupt controller level, and if you want to deal with I/O, also at the system level. Well, just a quick review also in terms of hypervisor spectrum. On one side of the spectrum, we have these traditional hypervisors, typically used in cloud and server settings. They typically feature a large code base. They typically may depend from Linux, which is part of this TCB. But they are fully featured. They have plenty of features for communication, for networking, for drivers, but they have this kind of high overhead I/O, which means that, okay, they have performance impact, and they have TCB impact in terms of security. Large code base means more prone to bugs, which means more potential vulnerabilities, but they are really fully featured in that sense. Well, a second class of hypervisors is these embedded hypervisors. Well, they present a reasonable code base, typically TCBs ranging from hundreds of Ks to tens of Ks. And they provide some sort of soft real-time guarantees, but they have this kind of scalar where you can basically provide multiple virtual CPUs atop one physical CPU. A good example is RISC-V, just for reference, because we will see during this presentation. By the way, these hypervisors highlighted in blue, you will see later on that they fully support the RISC-V hypervisor extension. So another kind of topology is this kind of microkernel hypervisors where they leverage this secure by design approach. Some of them are formally verified, like CL4, and they resort to capabilities and to basically provide additional security guarantees. What they need is they typically just provide a minimal sort of TCB on the hypervisor mode, but then they need to provide these virtual machine monitor capabilities as kind of user mode. And this has some impact in terms of performance and interrupt latency. And the best example is CL4. Well, on the other complete side of the spectrum, we have this kind of zeitgeist in terms of mixed criticality systems, which are the static partitioning hypervisors. These hypervisors are quite minimalist. They are really small because they basically define, allocate, and establish the system at design time. And you cannot schedule or modify during runtime. But they provide strong isolation and real-time guarantees, but they have a kind of inefficient resource usage because you cannot manage the resource during runtime. And a good example of this kind of hypervisors is BAW. You will see what is BAW in the next few slides. So this was pretty much a very quick overview around virtualization techniques, topologies, and different hypervisor designs, and covering the hypervisor spectrum. So what we'll discuss now is the RISC-V hypervisor extension. This extension is the hardware virtualization support at the CPU level, is part of the privileged architecture, and what we will do first is kind of review what is the base privilege architecture in terms of privilege modes. So in a RISC-V core, when we want to run Linux, we have 3 privilege modes. We have the machine mode, the supervisor mode, and the user mode. And each of these modes is set of CSR, control stat registers. In terms of memory isolation, in this basic setting of the privileged architecture, we have the PMP control, or the physical memory protection, controlled by the M mode. And we have this space-based virtual memory controlled, or the memory management unit, by the supervisor mode. And the good thing of the RISC-V architecture is that it is classically virtualizable. If you remember well what I just introduced minutes ago, which means that all sensitive instructions are privileged instructions, which means that if we want to virtualize the architecture, these instructions, we can deprivilege the operating system to user mode, and then basically run the hypervisor in supervisor mode. And you can trap and emulate everything. Well, the hypervisor extension was introduced in the privileged architecture, was fully ratified by the time of the last year RISC-V summit, is well designed, well suited, well specified for type 1 and type 2 hypervisors, is based on the concept of orthogonal execution modes, and basically you have this hypervisor extended supervisor, and then the virtual supervisor and the virtual U mode. We will see in a second. And it introduced a couple of additional CSRs and other modifications to the memory subsystem. Well, this is the augmented view of the privileged architecture that we have seen in 2 or 3 slides ago. So here, what we can see is that this supervisor mode is augmented for this hypervisor extended supervisor, and we have this virtual supervisor where you can run the guest operating system, and the virtual user where you can run your guest user space. And it's pretty much, and it is quite orthogonal because it's well designed in the sense that if you want to run the normal operating system and you don't want to leverage the hypervisor extension, you can just run perfectly in AJS mode because it behaves like supervisor mode when the virtualization stage is not active. Well, part of this extension starts with the control status registers. We have hypervisor and virtual supervisor CSRs, hypervisor CSRs for hypervisor capabilities, virtual supervisor CSRs for guest access. And just for reference, on the right side, I listed all the registers in terms of HS and NVS mode. And quite interesting, if virtualization is disabled, like V equals to 0, in HS mode, like the registers with the prefix age basically are for hypervisor capabilities. Then you have the virtual supervisor for the guest state, and if you use the S prefix, basically you point to the standard S mode CSRs. However, when you have the virtualization stage active, when you are in VS mode, you refer to the S register as a shadow copy of the supervisor registers, but they are in fact virtual supervisor CSRs. And the specification also augments the machine mode CSRs with a few couple of bits to support this virtualization stage. Well, the hypervisor extension also defines a couple of instructions. 3 are related to the hypervisor VM load and store instructions. These HLV, HLVX, and HSV with different semantics. And basically, these instructions allow you for an hypervisor to access the memory as it was enforced by the policies in VS and VU mode. The specification also defines a couple of fence instructions that you can use to enforce order in memory, and they are listed here. Well, a quite significant part of this hypervisor extension when you are implementing in a core is also the memory management unit. So in a traditional privilege mode, privileged architecture, when you don't have the hypervisor virtualization support, your MMU is single stage, which means that you translate host virtual address to host physical address. When you are running multiple virtual machines, you need a second stage of translation where you basically exercise guest virtual address to guest physical address, and then the second stage goes through the guest physical address to host physical address. And also related to the MMU subsystem, there are different options for the translation scheme. You have this bare option where the guest physical address are equal to the physical address. But when we have the G-stage translation in place, there are different configurations or different options for the virtual space. And I have here in blue the SV39X4 because it's related to this image. This image tries to illustrate how the process is done going through the page tables and through the G stage. In this particular case, we have, till the end, we have the 3 stage. Basically, if you are not leveraging the fine grain level of page tables, if you are having, for example, huge tables, at the second round circle, we just go to the next stage. I think this image pretty much illustrates what is this address translation scheme. Well, the hypervisor extension also augments the traps. The traps encoding, there are a couple of encoding cores added to the specification, but also augments the trap entry and return logic. Something important that we will see later on the presentation is this concept of transformed instructions. We have seen that RISC-V is classic virtualizable, which means that when in user mode we are trying to access a privileged instruction, it will trap to the hypervisor. But this optional feature of the spec, what gives you is that it provides additional information about which instruction generated the trap, which basically speeds up a lot the process of understanding what was the instruction and what I need to emulate. Because if you don't have that information, what you need to do at hypervisor level, you need to understand the address that triggered this exception. You need to go understand what are the instructions that triggered this extension. You need to decode the instruction, and then you need to emulate and provide the information. So if part of this process is already done by the hardware, it's much easier, and the process of trap and emulation is more lightweight. And on the right, what I have is a table of the transformed instructions. In this particular case, I got this table from one of the implementations that we did in a real RISC-V core. I will speak about that in a moment. Just checking the time. OK, and there are a couple of extensions that are quite important for virtualization. One of these extensions is the SSTC, which basically provides a direct access, for example, for the VS level and for the hypervisor level to get the notion of the time, because if this extension is not implemented, the time needs to be provided by the machine, which means that you need to have additional traps just to have the notion in terms of time for your virtualized environment. And there are a couple of other extensions related to cache if you need to implement smarter and more advanced mechanisms in terms of cache management to not basically have side channel attacks and all of that stuff. Just for reference, I have all of them here. Well, I basically overviewed more or less with the specification, the RISC-V hypervisor extension. So what I'm doing now is to provide the audience with the big picture in terms of the hardware and software ecosystem. So this image is from the presentation from Philip and Mark last year at the summit. I think you can see in the middle one rectangle that says hypervisor, and you pretty much see 3 logos. And these 3 logos correspond to these 3 hypervisors. So as of today, those are the 3 main hypervisors that have fully support for the RISC-V hypervisor extension. KVM, I think you are pretty much aware or familiar with KVM, is a type 2 hypervisor based on Linux, widely used in enterprise virtualization setups. And also XVisor, developed by IOMMU, is a type 1 hypervisor, monolithic architecture for soft real-time embedded applications. And these 2 hypervisors were the main drivers of the specification. But then we have BAU. BAU is a type 1 static partitioning hypervisor. It was developed and started by my team. And basically, it's for mixed criticality systems, and we have been helping also with the hypervisor extension, and we run BAU in different RISC-V cores with virtualization support. You have, for each hypervisor, you have also the link if you want to check on GitHub. All of them are open source. What I have here is a more comprehensive view. I tried to scope more projects, what is the status of these projects, what are the license of these projects, and try to provide some reference if you are interested on. So in the top 3 lines or rows, we have the 3 hypervisors that I just mentioned. Then we have Zen, is also quite famous hypervisor, and JLAWs that are at the moment extending support for RISC-V. CL4 requires the CL4 virtual machine monitor. There is a proof of concept from Yan, and yeah, there is a link there. Rivus is also developing this Salos hypervisor, mostly in the context of the TE, the confidential computing work that is being done. There is also some commercial options that I believe they are work in progress or near to complete. It's quite interesting because if you go to the website, they say that they support, when you check the BSP, there is no BSP for RISC-V, so it's pretty difficult to understand what is the status, but I believe they are working on that. And sorry if I miss any hypervisor, and feel free to ping me if anyone has another option that could potentially fit here. Well, this is pretty much the software status in terms of hypervisors that support the RISC-V hypervisor extension. There are a couple of emulators and simulators that you can leverage to also test the hypervisor extension. We have Spike, is the golden reference functional RISC-V ISA software simulator. We have IOMMU, which you should be pretty familiar to you as well, and we have this free option from Imperas, but you will need the Pro version if you want to test the hypervisor extension. Well, a bit more interesting, understanding which RISC-V cores have this hypervisor extension. My team was quite involved in the implementation of the extension of 2 RISC-V cores with hypervisor extension. The first work was presented in the RISC-V Summit in 2020, where we presented the very first implementation of the hypervisor extension in a real RISC-V core. It was back then the Rocket core. We didn't upstream that implementation. Andrew from Sci-Fi and his colleagues then take this implementation as the basis and basically implemented and upstream a derived implementation from ours in the Rocket maintained by the Ships Alliance. Over the last year, during 2022, we have also implemented the hardware virtualization support in the CVA6. The CVA6, it's maintained by the Open Hardware Group. This core comes from the Ariane, from the Pulp team, and is now maintained by the Open Hardware Group, and my team has fully implemented the hypervisor extension in this core. If you want to run, I will run a demo with this core in a few minutes, but if you want to have a pointer, you have there a pointer for a tutorial. Then there is another commercial slice GPL version, which is the NoL5 from COBAM. It's mainly related to the de-risk European project. And I'm pretty sure you have been here around, and there is the Sci-Fi core, the Starfi core, there is now the Ventana core, the very own one. They are commercial options, and they fully support the hypervisor extension. And there is also these chromides from in-core semiconductors, open source. They are kind of Sci-Fi from India, and basically they are extending or finalizing the support for the hypervisor extension. I'm pretty sure about the status of this work because we have been in touch with them. And also there is the Shakti project, a kind of initiative in India as well, that they told me that they are near to complete the support as well. Once again, if you are aware of other cores that potential fit here, please let me know. I have been scoping the different stands from the different design manufacturers and silicon manufacturers, and I couldn't find much more information. Well, a quick reference. I have been involved in a project where we implemented the extension for the CVA6, the hypervisor extension. This core has been plugged in a test chip, an SoC. This project has been funded by the TII from the UAE. You probably saw the booth from TII in the Expo Hall yesterday or before yesterday. And this is an SoC specifically developed for UAV drone applications, with the main driver is security as well. And this is a test chip that just came out a few weeks ago. They are testing. We implemented the hypervisor extension, and we are expected. This one is single core. We are expected to produce a second version next year with a dual core configuration. Well, this is pretty much what I have in terms of hypervisor extension for the theory, or the theory plus the pointers. So what I'm going to do now is a set of demos related to the hypervisor extension. My intention with the demos is to provide the audience and all of you with the right pointers if you want to duplicate, replicate, if you want to try by yourself. For each demo, I try to explain what is the intention of the demo. In this one, demo one, run KVM on IOMMU, and I try to provide the different pointers for the different artifacts that I'm leveraging. The correct version, the links where you can pick these versions, and to be completely precise, the exact commit that you need to plug so that everything fits magically together. So this is the flow that you need to follow to replicate the demo. A quick note, there is a link below the demo. This link is expected to provide the right instructions with a bit more detail. So the idea for this demo, the steps that you need to follow is basically you need to build IOMMU. I have already built IOMMU with the hypervisor extension support. It's already upstream. Build OpenSBI firmware, which is the machine mode firmware that you run on the iOS privilege mode of of your system. Then build Linux kernel, either the host and the guest, because we are running KVM. KVM is the virtualization on Linux. Build the KVM tool, build the Linux kernel host root file system with the different components, and hopefully now I run the full setup with IOMMU. So the output will be similar to this one, but I will do live for you. So I think you can see the screen. I will just get my script. OK. So what I'm going to do is I will explicitly call IOMMU with a specific parameters. I feed IOMMU with the BIOS or the OpenSPI. I explicitly feed with the kernel image, the root file system, and a couple of commands. And basically, if I press start, yeah, Linux is booted. But let's get here. So when we run the command, it will start OpenSPI. In this particular case, we can see that the platform is from IOMMU. We have one ART. ART means hardware thread in the RISC-V lingo, which stands for CPU. Basically, we have one CPU. And yeah, we just start here Linux. And we can see that we are running Linux. Just for the sake of demonstration, I can run the CPU info, and we can see that we have one ART as the output of OpenSPI, and we have the age extension according to the naming of the ISA, basically. And we are enforcing the SV48 virtual space configuration. So this is pretty much the demo for KVM. And I just now need to install the model of KVM. So I just boot Linux. KVM runs atop Linux. So I'm inserting the kernel module for KVM. OK, it's done. And now I just need to start basically the KVM to run one guest operating system with the different information. So what I'm doing now is running another Linux guest operating system atop KVM, which is part of Linux as well. So yeah, we have booted also the guest operating system. And if we do, again, the cat CPU info, we can see that now we have two virtual CPUs running atop one physical CPU. So this is pretty much the demo for KVM. Let me just go ahead. So the second demo is about running RISC-V. RISC-V is that other hypervisor developed by IOMMU that targets embedded systems, soft real-time guarantees. And once again, I provided all the info that you need to run RISC-V. The link with more instruction details, and the different steps that you need to follow to basically replicate this setup. So once again, I have compiled everything because we didn't have time to go through compilation steps here. So I'm just running the final command, which will launch RISC-V as a bare metal hypervisor. And then once we have RISC-V, we will run a Linux guest operating system. And we will have an output similar to this one. OK. Once again. So I'm running, again, IOMMU with a specific configuration. The BIOS is, again, the OpenSPI firmware. The kernel now is different because it's the VMM from RISC-V. And then I feed with the other parameters that are needed. And yeah, I just started RISC-V. if you see here again on the OpenSPI, one art, and Hypervisor starts here. This is the log of Hypervisor, and then is the logo of Hypervisor. Now I just need to kick guest 0. Let me check. Yeah. Guest 0 is kicked. Now I need to bind the UART to guest 0. Okay, it's binded. And now I just need to start this guest and start booting Linux. So what we are seeing now is Hypervisor is a type 1 hypervisor that runs directly atop the hardware. The hardware is IOMMU, is the virtual platform from IOMMU. And once Hypervisor is booted, I create one guest, and this guest is a Linux guest, and I start and kick Linux atop Hypervisor. And you can see here, once again, yeah, 2 virtual arts atop 1 physical CPU. And this is for Hypervisor. Okay, so the third demo is this BAU hypervisor. This BAU hypervisor was developed by my team. Once again, I provide the different pointers for the different components so that you can try by yourself. In this particular case, we are doing something a bit more interesting. Instead of running just one single guest operating system, we are going to run 2 operating systems. On one side, we have FreeRTOS, a real-time operating system. On the other side, we will see Linux as well. So I will have 2 terminals. On the right side, I will display basically the FreeRTOS, and on the left side, I will run the Linux guest operating system. So these are the steps that you need to follow to replicate, and I have compiled everything, I've prepared everything, so I will just run the configuration and the setup on IOMMU, and hopefully we will get something similar to this. On the right side, starts the OpenSBI, BAU hypervisor, and immediately leverage the same UART to deliver for the guest the real-time operating system that will print message every second and receive some interrupts when I press the keyboard. On the left side, I will run Linux. Okay. So a bit different. I will need 2 command lines. Let me. Okay. Here I'm preparing already screen. PTS, because I just need to pick the number of the output when the IOMMU starts. So at the moment, OpenSPI has booted, BAU hypervisor as well, and then BAU starts the FreeRTOS guest, and the FreeRTOS has 2 tasks. Each task is printing every second. And when I basically press a key, it handles an interrupt. So I just need to pick this PTS2, and hopefully we have already, Linux has already booted. I have a root account, root, very difficult password. And now, sorry, I'm here on Linux running as a second virtual machine. So what I have now is a system with a bare metal or type 1 hypervisor running atop the IOMMU virtual platform, and this hypervisor is managing 2 guest operating systems. I have 4 ARTs or 4 CPUs. The Linux has 3 CPUs. We can count them here, 3 ARTs, and the FreeRTOS manages the other CPU. And if basically I shut down one operating system, like Linux, FreeRTOS just runs normally. I mean, if an hacker attacks the Linux, it cannot impact the FreeRTOS. This is the beauty of virtualization, provide time and spatial isolation. Okay, but now I have something a bit more interesting to close the demos related to this part, which is I have here an FPGA platform, okay? So this FPGA platform is already with a bit stream. This bit stream is running this CVA6 RISC-V core from Open Hardware Group. And basically, this core was extended by my team to include Hypervisor or the virtualization support, the Hypervisor extension. So what we are going to see is basically, maybe I should adjust a little bit the setup. Okay. So I have here the different pointers because now if you want to replicate the full demo, you need also to compile the core, not only the software. You need to compile the hardware, all the pointers that are needed, all the flow that you need to go through so that you want to replicate. Of course, I have done almost all the work. I have burned the bitstream in the FPGA platform. And what I'm going to do now, and hopefully this will work pretty fine, is to basically power the platform. Let me try. Connect the UART terminal. Okay. I will stop this demo. I will launch screen. TTI 0 is outputting a. Okay, now it's just copying the image to the memory. Let me just. It takes a bit of time. It's basically copying the image that is in the bitstream to memory so that it can run Linux. This system basically consists of CVA6 core in a specific platform. It's a couple of peripherals or device. And then BAW hypervisor on top of that. And then in this configuration, because we don't have two UARTs, two different outputs, I'm just running one single guest operating system, which is Linux. And we will see basically Linux going. So BAW hypervisor now starts, and we'll launch Linux. We are now seeing Linux live going atop a real RISC-V core. So it's not super, hyper fast because this is an FPGA platform, it's not ASIC. But yeah, hopefully we get through the end of the boot process. Just a few seconds more. Yeah, and we are here. And I'm running Linux. And now what I can do, I can play Tetris. So I'm running Tetris live here atop a RISC-V core that is running in a guest operating system on top of Linux and BAW. Okay, so yeah, it's pretty much that part as well. So I have covered 4 live demos, different hypervisors running atop of IOMMU, either atop an FPGA platform that runs a real RISC-V core. So I'm preparing for the next one. Okay. And yeah, it's the output. So this was basically the hypervisor extension. So now I'm shifting gears towards the RISC-V advanced interrupt architecture. I'm already a bit late, so I will try to speed up a bit. So the RISC-V AI is the new advanced interrupt architecture. So the existing PILIC in most of the RISC-V platforms, the interrupt controller existing in most of the RISC-V platforms is the platform level interrupt controller. It's simple, but it has some limitations in terms of scalability in particular. I listed here some of the limitations, and I highlight, for example, the lack of support for interrupt virtualization and the lack of support for MSIs, message signal interrupts, in particular when you want to have HPC setups. This is quite meaningful. Well, over the last 1.5 years, I would say, it has been extensively discussed, this advanced interrupt architecture. It addressed the limitations of the PILIC. It provides scalability for a large number of ARTs. It provides MSIs, APIs. It provides support for virtualization through MSIs. And it is mostly three main components. The extension or the augment of the CSRs is the advanced PLIC to manage wired interrupts, and is the incoming message signal interrupt controller, the IMSIC. This specification is in version 1.0 RC1, is in public review at the moment, and the target is to ratify till the end of the year. Well, this is basically, if you check the spec, this is a table that you can find on the spec that pretty much clarifies the status of each of the chapters and the status of the specification. In terms of CSRs, once again, just for reference, I list all of them here. CSR spans across machine supervisor and hypervisor and virtual supervisor. We have a couple of virtual instruction exceptions, and these lead to the two new ISA extensions, the SMAI, SSAI, which defines the CSRs and a bit of logic for the different modes. Well, in terms of components, the APLIC is the one responsible for handling wired interrupts, basically you can find organized in terms of interrupt domains. One domain is associated one privilege level, and you have the option to configure priority, target, line sensing. The limits of the APLIC is 123 interrupts, and the number of ARTs, as you can see, is really big, 16,384. It's a memory mapped control region per domain with optional IDC structures, and it can basically operate in two different modes: direct mode, when you directly deliver the interrupt to the ART, or MSI mode, when you forward the wired interrupts as MSIs to an ART leveraging the IMSIC infrastructure. Well, in terms of IMSIC, there is one IMSIC per ART, which means if you have a configuration with, for example, 4 ART or 4 CPUs, you will have one IMSIC per CPU, which typically, in terms of placement, is coupled to the CPU. Each IMSIC provides n interrupt files, and in the sense that you provide one for M mode, one for S mode, and n for VS mode. And this is defined while you are doing your design. The IMSIC supports message signal interrupts, was one limitation of the PILIC, and the virtualization support that exists to deliver interrupts directly to the guest without any kind of hypervisor intervention is through this IMSIC infrastructure. Well, in terms of virtualization support, you have different CSRs extended for the guest and for the virtualized interrupts priorities. In terms of IMSIC virtualization, as we see, we have multiple VS interrupt files or guest files per ART. This is defined in the design. One VS file can be linked to a virtual CPU in the G-stage translation, and you have different management options. And you have also the APLIC virtualization, as I said, in terms of direct mode, you need to trap and immolate everything, and this is quite costly. I will get there. Or when you have the IMSIC infrastructure, you have this MSI mode, which basically you can redirect wired interrupts, then translated to MSIs directly to the guest operating system. So I want to highlight this slide because the idea here is to highlight for the fact that, okay, you may have designs where you don't have the IMSIC At the moment, the spec says that when you have the hypervisor extension, they assume that there is IOMMU so that you can directly delegate and forward the interrupts directly to guests without any hypervisor intervention. But as we will see at the end of this part of the presentation, this is still a topic of ongoing discussion to understand if the APLIC will exist as a single component without the IOMMU in some configurations, and in that case, what kind of support is needed. So I just want to highlight basically to highlight how impacted will be the interrupt latency and performance in case there is just a system with the APLIC and in case there is no support for virtualization. And this is pretty much the flow. So you get a wired interrupt on this one on the bottom. This goes for the root domain or M mode domain that can delegate to the S domain and delivers to the S level ART. That is responsible for then interrupting the guest operating system to basically, on step 4, inject the interrupt for the guest. So in step 4, it claims the interrupt, and then it injects the interrupt for the guest. But the problem is the guest doesn't have access to the APLIC, direct access to the APLIC, which means when the guest, because it's running blindly, needs to claim the register on the APLIC, needs to trap to the hypervisor so that the hypervisor can emulate this feature and basically deliver the execution again for the guest. As we can see, this is pretty much the complete flow, which means there are a lot of traps while receiving and acknowledging and handling an interrupt from a guest perspective. So, and this is the time in terms of the flow in terms of time so that people can understand what are the different operations. I will get there because I have a demo just to explain this thing. And yeah, with the IOMMU, this is pretty much simplified in the sense that, yeah, the MSI delivered through the IOMMU arrives to the IOMMU directly to the interrupt file that is responsible for directly delivering the interrupt for the guest. And this is a very smooth and very fast process. Well, in terms of software and hardware status, this is pretty much what you can find out there. In terms of software, software is upstream in IOMMU, is upstream also in OpenSPI, the support for the AI. It's complete in Linux and KVM, but it's not upstream yet. That's why the reference branch are from ANOP, not the main branch. And still, the other two hypervisors that I was mentioning so far, like Xvisor and BAU, ANOP is implemented at the moment, expecting, according to what I spoke with him, to be complete by Q2 2023. And my team also is working on that, and we are expecting more or less for the same time frame to complete the support for the AI. In terms of IP, hardware IP, I can say that if you are going to read the spec, there is a note that says that it is very likely that an APLIC, not the full AI, IP, a system Verilog implementation of the APLIC will be provided under a very permissive license. John Hauser, which is the main driver of this specification, I have spoke with him yesterday, he's still committed to do that, apparently around end of Q1 2023. This is a reference IP that people can leverage. My team is also implementing this AI. The APLIC is already implemented. Is distributed under the Apache 2 license, very permissive. So if you want to pick this IP to put on your designs, you can do it. We have the reference. It's not fully tested. We are going to start the testing process. And we are also committed to implement the IOMMU and the full AI by Q2 2022. Sci5 and Ventana claim, and you could see on their booth that they have already with these new designs the full support for the AI under commercial license, and COBAM is expected to release under commercial license in Q1 2023. You have some reference here as well. Well, this is the point that I was highlighting before, which is this is still a topic of ongoing study and discussion to understand the different trade-offs in terms of if there will be systems to manage wired interrupts with uplink-only systems, or what are the costs of augmenting the uplink for virtualization support, comparing with some designs leveraging the IMSIC. This is a study that I'm interested from my side, at least from my team, and I have aligned with John with regard to a potential study and try to understand the different trade-offs on this. So now what I need to save a bit of space here. So I'm running 2 demos regarding the AI. So the very first demo is to run BAU already with the uplink driver support, so without the IMSIC. And what I'm going to do is basically to debug live so that you can understand this flow that I was referring. So when you just have an uplink-only system, what is the performance impact and the expected interrupt latency, because you don't have any sort of virtualization support. So, okay. Let me just. Okay. RISC-V on Linux GDB. I'm running. So what I will run here is on the right side, I'm running BAU with a simple bare metal application that handles one interrupt. Okay. On the left side, I will run debug the execution flow so that we can see the number of traps to handle one single interrupt. I will just get my script here to launch. Okay, so okay, I started the debug session. This is kind of GDB on steroids. And what I will do, I will load the L file with the symbols so that we can debug. So I will put a breakpoint, be init, on the init of BAU. This is the initialization function. So I will C to continue the execution flow. Okay, and it stops. So right now, we just started OpenSBI with 4 hearts, 4 CPUs, and we are still initializing BAU. So since we have 4 CPUs, this function will execute like 4 times, okay? I will continue, 2nd time, 3rd time, 4th time, okay. Now the 4 CPUs are up, BAU was booted, and we have the bare metal test guest. This bare metal test guest running on top of BAU is just handling one simple interrupt, right? So if I press a key, it says that it's handling a UART interrupt. So what I'm going to do, as I was saying, I want to illustrate this flow. So I will put a set of breakpoints. So one is this trap vector, is a vector in BAU, in the low-level exception code, okay? I can put, you can see the code. So it's kind of the VM exit is responsible for do the entry on the hypervisor and exit from the VM, okay? The second is vCPU, vArch entry, okay? And this is responsible for doing the exit from the hypervisor and the entry for the virtual machine. And I will put a breakpoint on the v-applic inject, which is the part that injects the interrupt on the hypervisor, on the guest, I would say, the injection. Okay, so what I'm going to do now is I continue the execution. So on this side, I press a key, okay, and here we go. So at the moment, we are executing the guest, and I press the key, I do an interrupt, so I will do a VM exit and an hypervisor entry, and we are here, VM exit, okay? So now I continue the execution, and it will stop on basically the applic injection. I will continue. Now I'm doing the VM entry or the hypervisor exit. So far, what we have done, we were here, we get here, we inject here, and now we are going to this level. Okay, we are going to basically run the guest again. So I do C. As you can see, there is no output still on the right side, which means the interrupt is not handled yet. So I continue, and now I'm doing another entry on the hypervisor, another exit for the guest, because I'm trying to claim the register on the applic, but since the guest doesn't have direct access, need to trap and emulate. So once again, I do the claim, and now I go again to the guest. So, and you see now the interrupt was handled. So this is the burden process, or the performance impact of basically trap and emulate everything when you don't have support on the interrupt controller, in this case with the applic. So this was pretty much the demo. The second, okay, this was the demo. So the second demo is to just run the KVM with the full AI support on IOMMU. Yeah, with these components, this boot flow, and I will close this terminal, get this terminal full, finished, okay. Getting my script. So I'm running again IOMMU with a specific configuration for arts. Quite important. The machine, we specify that it needs to have the AEI and the number of AEI guests and the different image that need to be fed. And yeah. Basically, we can see here that, okay, the API support is through the IMSIG, which we saw was one of the features that the PILIC didn't have, but that the AI brought. Processor interrupts with support through the IMSIG. We can see also here that while booting Linux, there is this IMSIG discovery. And if we do basically the output of the interrupts, we see that we have here the applic for the different wired interrupts. So this is the full support for the AI. Yeah, I need to run again because I need now to. So this is just Linux. I will now run KVM to run another guest Linux, and you will see where is it? Okay, apps in mode. Okay, I'm inserting the kernel model for the KVM on Linux, and you can see that, okay, we have the AI support. And now I just need to get the script to run KVM. Okay. Yeah. And you have Linux booting. So we are running a Linux guest operating system at top KVM, also with support for the IMSIC. Yeah, and it's pretty much. And if you want to change the configuration, for example, to test different setups in terms of AI support, you just need to change this part on while running IOMMU. You need, for example, if you want to run just a system with the APLIC, you can come here and remove this part, and you will see during the boot of Linux that the discovering of the IMSIC will not be shown. Okay, this is pretty much, I'm a bit delayed, I need to speed up a little bit. This is pretty much in terms of demos for the AI. So speaking a little bit now about the IOMMU, which is a quite very important component in terms of virtualization for enforcing policies on the I/O. So this is the motivation why we need an IOMMU, because your core is not the single master of the system. There is other bus master attached to the interconnect with some, for example, some device, some crypto accelerators, and this device can have DMA capabilities, which mean that they can directly access portions of memory. And if if you don't enforce permissions and access control at the bus level, basically you can have one guest operating system configuring one device to perform this memory access whatever you want. And basically, if you have a buggy driver, a malicious software, or a misbehaving I/O device, this is quite bad in terms of security. Well, that's why we need an IOMMU. The IOMMU enforce this kind of protection. In a non-virtualized system, it mostly enforces this protection. In a virtualized system, it also provides virtual address translation from the device itself, and, for example, interrupt virtualization support in the case of RISC-V. And in this case, an I/O device configured with a DMA is not able to access the memory more than the one that is permitted by the guest memory space. Well, yesterday there was a very interesting talk from VED in terms of I/O virtualization use case and RISC-V IOMMU. VED and Perrin are the shares of this IOMMU TG. So if you want to understand a little bit more the bits and the bytes of IOMMU, please watch the record of the VED talk. Over the last year, they developed basically the IOMMU specification. It progressed quite well. In 1 year, they reached almost a pretty stable version of this specification. Is now in version 0.9 and for public review and targeting rectification by the end of the year. In terms of comparing the AI with IOMMU, I will say that, and you will see in a minute, that the number of POC is still not so mature as the AI, but yeah, they are on track and in good shape for that. Well, I just list here the different features of the IOMMU. You are free to go to read the spec. This is just for reference. And the most important thing is that the IOMMU can just implement a single-stage translation, but when we are talking about virtualization, we need this two-stage address translation. And quite important is that this specification mandates that this translation should be compliant with the translation and definitions of the RISC-V privilege spec. Yeah. In terms of data structures, you have this kind of device context and process context. And this device context is quite important to provide or to specify the guest translation, which is this IO HGATP is equivalent to to the HGATP of the core. Is the G-state translation of the core, so they kind of provide a replica for the I/O. Quite important is that related, we will see in a moment, related to the MSIs, you have this extended format where you can specify the different policies for the MSI in terms of IOMMU enforcement. Well, in terms of interface, quite well defined, leveraging queues. These queues are command queues, fault event queues, and page request queues. And basically, this is the memory mapped register. Some are optional, like the performance counters. Some are not, like, for example, you can read IOMMU capabilities through this capabilities register, and you can interface with the different queues, like the command queue. You have the base, the head, and the tail in terms of registers. It's a kind of interface so that you can then implement all the logic for the queues in terms of the different commands. Well, in terms of virtualization, the IOMMU is flexible enough to provide, for example, on the left side, you have a simple pass-through configuration where one device is assigned to one virtual machine, and it basically enforces the right protection and the right access to the memory space of the virtual machine. On the right side, you have the illustration of a more complex configuration where you can have in place the dual stage translation or just the pass-through configuration, or either if you want to assign a device directly to an hypervisor and the hypervisor is running in the virtual space, you can also set the page table so that you can configure that. Well, there is a quite nice connection between IOMMU and AEI, in particular for the MSI support, because interrupts need to be redirected from the device to these guest interrupt files. As I was mentioning, there is this device context that holds the MSI-related data. I'm talking about this. This is where on your device context of the IOMMU, you can specify the different settings for the MSI. And you have two operation modes, the normal translation of address for MSI from device and the memory resident interrupt file. And basically, the memory resident interrupt file allows you to provide scalability not limited by the total number of guest interrupt files implemented by the IMSIC, which has an hard limitation for a 64-bit architecture of 63 or 31 for an RV32. And this basically provides a scalability method so that you can scale up more or the hard limitations. Well, in terms of software and hardware status, as I was saying, my impression is that it lags a little bit behind the AEI. There is a proof of concept with support in IOMMU, in Linux, but they are not upstream. I will show a demo prepared by Thomas from Rivus, where we run cross VM to run one Linux guest operating system with this support for the IOMMU and pass-through access to a specific device. My team is also first implementing one IOMMU IP and also the support for the IOMMU in terms of software on BAW. And also, Anup told me that once the specification is ratified, we will include support in RISC-V. And in terms of IPs, there is a repo from VED that has a very basic IOMMU RTL, not compliant with the specification, as far as I know. My team are developing this IOMMU IP, which we expect to provide under a very permissive license. There are the commercial implementations from Sci-Fi and Ventana in these very same cores that has Hypervisor extension and the AEI. And Cobham in the Noel, they expect to release somewhere in 2023 under a commercial license as well. Well, a kind of message. If you have attended the keynote from Manju on Tuesday, I got confused. I'm still in the jet lag. This keynote, she basically was claiming that we need standards. So there is a specification for the IOMMU. This image is adapted from his slide deck. We now have a specification for the IOMMU. It's important that different vendors, different players adopt this specification. What we have witnessing in other mainstream computing architectures is that sometimes there is an IP or a specification, and then OEMs try or silicon makers try to implement their own thing, and this leads to fragmentation. So this is a kind of call to action. And with that, I reached the part where I run the demo. I would like to thank Thomas from Rivus because this POC is still in development, and he took a bit of time to basically organize everything in a way that I could digest and I could replicate his setup. Here, what we have, we will run Linux atop IOMMU, and then the cross VM, which is a kind of implementation from Google, departing from KVM in Rust, is basically running another Linux atop this implementation, which implements the device pass-through for the device. So this is more or less the reference link, the steps, once again, and I will replicate the demo. So probably will not go through the end because this is basically Ubuntu running IOMMU. We will run Linux that with Ubuntu file system atop IOMMU that launch cross VM that will run again another Linux with Ubuntu. So you can understand the levels of indirections and that the performance is not super good. So now we start Linux, which is running Ubuntu with the Ubuntu file system. And I can, while it's booting, I can show you here the IO part, IOMMU. Yeah, we have here the log from Linux with IOMMU support, the different device with PCI. Okay. While I'm already. Takes a bit of time. Okay. I'm just listing the device with IOMMU that we saw on the log of Linux. I will just export a bit these configurations, and I'm running now cross VM. And cross VM basically will boot another Linux that will launch Linux with the Ubuntu file system and with the pass-through access to this device. So it will take a bit of time, so I just stop here. Okay, and with that, we go to the last part of the presentation, which is nested virtualization. Quick overview about nested virtualization. What is nested virtualization? For those that are not super familiar with that, is the virtualization of virtualization. It is the point where in your system you are running one hypervisor, but you want to run another hypervisor atop your hypervisor. And this is quite important for cloud providers in terms of infrastructure as a service in different use cases, ranging from full stack deployment, mobile app development, testing and validation, and either for education and training. Basically, if your infrastructure is leveraging an hypervisor so that you can run multiple virtual machines. And if you want to deploy in a cloud provider that is already running virtualization, so you have this kind of two-level virtualization. And this concept of nested virtualization is not only for two levels, but in theory for multiple levels. So there was a very interesting talk from Anup yesterday. Anup is the main driver behind virtualization in general in RISC-V, but in particular in implementing the proof of concepts for nested virtualization. So definitely we should see or watch the recording to understand a little bit more the bits and the bytes about the nested virtualization implementation in RISC-V. And this is more or less what we have in terms of architecture. We kind of create virtual modes in VS mode so that you can create this notion of nesting, but this is just the virtual view, because in fact what we are doing is multiplexing this VS mode and context switching manually the different components and settings. And this is done through mostly through, as of today, through trap and emulation, the concept that I presented at the beginning of the presentation, and is widely facilitated by the fact that RISC-V is classically virtualizable. In terms of MMU, you kind of, if you have two levels of nesting, you kind of need 3 stages of MMU, of translation. So, but you just have, in fact, on the hardware, two levels of translation. So what you do is a technique called shadow page tables, where you basically emulate another translation, and you need to go through software techniques to arrive and to create this shadow HGATP. Well, yeah, we leverage trap and emulation and shadow page tables, and if you want to understand the bits and the bytes in terms of nest switching, nest entry, nest exit, and lazy trapping, in terms of nest virtual interrupt, nest page faults, you should definitely watch the record from Anup. I will not go through the details. At the moment, as I was describing, nested virtualization support in RISC-V is mostly through trap and emulation, which is quite facilitated. Why? Because RISC-V is simple, RISC-V is classically virtualizable, because we have these transformed instructions that I spoke at the beginning of the presentation that are optional, but when we want nested virtualization should be mandatory. But this kind of trap and emulation for nested virtualization support has some limitations. For example, the impact in terms of performance. The real impact is still to be understood because we don't have real silicon. The TCB is maybe also a problem. More code is more bugs, is problematic for security. And at the moment, to be easier to implement this trap and emulation support, Anup limited this to SV39X4, which is 3 levels of translation. What has been decided in the Hypervisor special interest group is that to accelerate basically this nested virtualization support, they are going to create the SBI nested acceleration extension. But this basically consists in modifying the guest hypervisor to issue specific calls, and needs to be instrumented. Well, in terms of software status, you have already upstreamed the support on IOMMU, the support on XVisor, in terms of trap and emulation, and ongoing work in terms of this SBI and ACL extension, and there is work in progress on KVM as well. So this is a final call to action in terms, if you want to discuss more about nested virtualization, please join the Hypervisor special interest group. Please feel free to help with different POCs, and please feel free to research and provide additional additional ideas, either for in terms of hardware or other ideas that you may have, because other mainstream architectures has some hardware support for nested virtualization. So I don't have a demo because Anup yesterday, while doing his presentation, presented a very comprehensive demo, so I didn't want to replicate what he did. So if you want to see the demo, please watch the recording of Anup. And with that, I think I reached the final of my presentation. I want to give some credits to this very impressive team, my team that has been helping me to put everything together. A big thank you for them. And with that, I complete. And if you have any particular question, I'm happy to address.